Hello and welcome to another video on orbital mechanics. I'm still going through the book Orbital Mechanics for Engineering Students by Howard D. Curtis, 4th edition, and I'm up to hyperbolic trajectories. So I thought it would be good to go over the theory on that. The last video I did yesterday on parabolic trajectories, and I also did one on elliptical orbits in very similar format, and I think they went well, so going to do another one. So hyperbolic trajectories. So this is the point where your eccentricity is greater than 1. So a circular orbit eccentricity is 0. An elliptical orbit eccentricity is greater than 0, less than 1. And a parabolic eccentricity is equal to 1. And hyperbolic eccentricity is greater than 1. And what happens when it becomes greater than 1 is we get an interesting kind of visual occurring in the mathematics of it. And so you have the object coming in here and leaving here on a I guess a wider trajectory than you would have for a parabolic. As E increases, this line becomes closer to the vertical, and the way the properties work themselves out in a hyperbolic form is that your center of your orbit is here, your focal point is here, your mirrored focal point is over here, and your semi-major axis is from here to here, your minor axis is from here to here, and so that's A and B. So there's A and there's B, and then you have this beta angle here, which is also here and here, and then a gamma angle here. No, sorry. Delta angle here. And that delta angle is also down here, delta over 2. And it's actually, in my opinion, referring to this line, rotation into here and rotation out of there. That's the angle. It's also that angle there eventually. And so what can we say about some of these bits and pieces? So we can say that delta is 180 minus 2 beta. We can say that B equals A tan beta. And we can also say that beta is 180 minus theta infinity. Now theta infinity, this equation here, which applies to all orbits. If this denominator here was 0, r would be infinite. So what is the angle that happens at? So 1 plus e cos theta equals 0, r is infinite. So e cos theta equals minus 1, theta infinite equals cos inverse minus 1 over e. And if we use the rule, the identity sine squared theta plus cos squared theta equals 1, we can also get this here for sine theta. Just plug in those things into that identity and you'll be able to cancel out until you get this. It goes through it in the book as well, so a little bit of maths there to do if you want. And so here's your infinity, and then it's up here as well. Your RP, these are your standard ones. Yeah, these apply to all orbits, I think. 2a is equal to minus RA minus RP, because this RA is actually negative, because in other orbits it would be going this way, right? So in this case it's negative, and RP is in here, RA is here, so it's minus RA to drop the negative, minus RP to get to 2a. So there's your A, so that's 2a there. You can see it's that amount less that amount gives you this amount, so that's your 2a. So going forward, we have delta over 2 equals 90 minus beta, and that's just that. And then if we take the sine of both sides, we get the sine of delta over 2 equals cos beta. So sine 90 minus beta is the same as cos beta. And cos beta is equal to 1 over e, and so that becomes delta equals 2 sine inverse 1 over e. So this equation here is this one here, but we have taken this RA and RP and replaced them here and then extracted out the h squared over u. And then we rearrange that, you get A equals h squared over mu 1 over e squared minus 1. This is specific to hyperbolic trajectories. This is not very similar, but it is not the same as the elliptical one. And then rearranging that, we have A upon e squared minus 1 equals h squared over mu. And then going forward, so we can take that and we can replace the h squared over mu in this equation up here, which will then give us this. Here, r equals a e squared minus 1 over 1 plus e cos theta. Therefore, if you put in theta equals 0 for the periapsis point, you'll have rp equals a upon e minus 1. This expands out into a quadratic pair, and then one of those can be cancelled out. And the same for RA. You can cancel out one of the e minus 1 or e plus 1. So RP and RA are defined as such. And then this equation up here, which we talked about earlier, B equals A tan beta. Well, tan beta can turn into sine beta over cos beta. And then that can be described as this up here. So, yeah, sine 180 minus theta infinity and cos 180 minus theta infinity. That can become just sine, because this identity here holds, and this identity here holds, sine theta infinity and minus cos theta infinity. And sine theta infinity is over here, and minus cos theta infinity is effectively from this. You end up with a upon square root of e squared minus 1 over e, all divided by 1 over e, which the e's cancel, and you get b equals a square root of e squared minus 1. And then x here, so this is the point we're imagining on the orbit. It could be up here as well, if we've reflected it up, but this x position is the same thing going on with the parabolic trajectory, except we need to adjust the x position because this is the center of our x and y. So it's subtract that, and then it's this little component here represented by this, and then this amount down here represented by this. So that's your r cos theta, and that's your r sine theta to get to these positions. So, and then I haven't put anything else on here, but if you take A and RP and your R and use all these definitions and replace those, and then a little bit of, squaring both sides, etc., it's possible to get the right hand side of coses and sines to cancel out until they become 1. And that's quite detailed in the book, and you can go and see that. But safe to say is this mixed with all this, you can get down to this to find and replace and simplify. And then for the energy, so this is our standard energy equation here. And if we take the 1 minus e squared from this, I don't know, sorry, what is it? From here, right? So if we solve for 1 minus e squared and put in these components into here, it simplifies into mu over 2a. So a lot of stuff cancels. So the energy of a hyperbolic orbit is mu over 2a. And then we can use that with this equation here. That's another energy equation. The left-hand side of that equals this side, and this. So this we can turn this into velocity infinity, and we can do that by at infinity r is infinite. So if r is infinite, this becomes 0, right? And then rearrange, so you end up with a v squared over 2 equals mu over 2a, and that's the infinite velocity. And then you rearrange, the 2 disappears, you end up v equals mu over a squared. So then we can just leave that as squared and replace it there. So you end up with this equals v infinity. And then we also know that velocity escape equals the square root of 2 mu over r. So we can also put that in here. And when you put all that in, you can drop your 2's on the bottom, and you end up with v squared equals velocity escape squared plus velocity infinity squared. And all this is saying is that we have some extra velocity here that we don't need, but maybe some other reason the mission needs it. So this would be our sort of remainder. Maybe you can do something else with that. But realistically, to get in and out of orbit, we would only need this. Of course, having a bit more would change our trajectory as well. The more velocity you've got, the less of a parabola you're going to make. And if you're going at infinite speed, you would just be going straight. You wouldn't turn at all. You just blast right past it. So that's everything I'm going to cover so far on this one. I know that's quite a lot, and it's all over the place, but I'm just trying to keep everything on one page. And there is quite a bit for the hyperbolic trajectories, but in theory, it is the same as all the others. We're just, things go a bit mad when you go to different ranges, and we have different simplifications and ways to get to answers that are useful, but it's essentially just a lot of trigonometry. So if you think I've made a mistake, let me know. If you have any questions, let me know. Otherwise, thank you very much. Goodbye.